Okay, so in this video, we're gonna talk about a second method of proof, which is proof by induction. So I'll show that to you with an example. So here's an example I want to use to understand the mathematical induction. So suppose K is a positive, I guess is an integer more than 1. Prove that for every integer n positive, there are integers a0 all the way to ar such that they're all inside the set 0 all the way to k minus 1, such that n is equal to a0 plus a1k all the way to ark to the r. So this means you can write down n in base k. So I want to prove this statement, which is why you want to make sure that your base is more than 1. Okay, so what is the proof of this statement? Okay, so the first thing that I do is always to write down the method of proof at the beginning so that it is clear what we are doing. But before I write down the method of proof and before I actually obtain a solution, I'm going to start trying to figure out what I should do and why I need to use mathematical induction. So I'm going to first start with the sketch of the solution. So imagine if I want to write down n in some base. So let's just look at 143 and let's say k equals 4. So I want to write down 143 as sum a0 plus 4a1 plus 4 squared a2 plus a bunch of other things potentially. So I want to understand what these a1, a0, a1, a2, and so on must be. So after pondering a little bit, we realize that, and we know all of the AIs are 0, 1, 2, or 3. We realize that this portion is a multiple of 4. Which means this guy is the remainder when you divide 143 by 4. So this is the remainder when 143 is divided by 4. So that is nice because now I can figure out what a0 is. All I do is I take 143, divide it by 4, so I get 4 times, so if you divide that by 4, you get 4 times 70. No, you get 4 times 35. So that's the quotient. 35 is the quotient because 4 times 35 is going to become 140, and the remainder would be 3. So this would be our A0. And then to get the A1, A2, and so on, I have to take this portion and then write that one down in base 4. So write this in base 4. Okay, so what's the idea? The idea is start from a larger number, 143, reduce it to a smaller number, in this case 35, and then repeat the same process for 35. So that's the idea. In other words, you're doing this, you're building blocks on top of the previous blocks that you have already built. So it's like building a building, but each block each brick would be on top of the something below it. So that is the idea of mathematical induction. So the idea is start with the base case, start with proving it for the smallest possible value that you are thinking. In this case, it would be, because they said positive integers, you start from 1. And then after you prove it for 1, then you assume it is true for n, and then you prove it for n plus 1. So there are 2 steps for that. So basis step would be prove for n equals 1, and then inductive step would be assume for n and prove for n plus 1. So that's the general idea of mathematical induction. So we'll employ this idea and we'll write it down very clearly for this particular problem. So here's the solution now. Going back to the problem. So again, the main idea of mathematical induction is that you're relying something on a previous case. That's the key idea. So we will, again, I will specify at the beginning of the solution that I'm using, we will use the mathematical induction. We'll use the method of mathematical induction. So what I do is I'm going to just write down the basis step, write down the inductive step, and then that would be it. So we will use method of mathematical induction on n. So I'm going to specify what variable is the variable that I'm using induction for. So basis step. In fact, I can prove this one for any n that is less than k. So if n is less than k, then a0 equals n and r equals 0 gives us n equals a0, and we are done. So anything less than k, we could prove it easily. So now the inductive step. So what we do is we're going to take n, divide it by k, get a quotient, get a remainder, and then move on from there. So suppose, since I proved everything that is less than k, now suppose n is greater than or equal to k. Now by division algorithm, there are integers q and a0 such that n is equal to kq plus a0 with a0 between 0 and k. Okay, so we have that. That's by division algorithm. That's kind of the long division that you have learned. Then we now know that q, I'm going to apply inductive hypothesis for q. So q is less than kq because k was more than 1, which is less than or equal to kq plus a0, which is n. So now by inductive hypothesis, q is equal to a1 plus a2 r, what was it? No, k was the base, all the way to ar, k to the r, for some ai between 0 and k minus 1. Thus, n becomes a0 plus a1k all the way to ar k to the power of r as desired. And that completes my proof.